Welcome to the Deep Dive. Today we're digging into some really interesting academic papers. Think of it as an essential study guide to two key concepts in modern computing: concurrency and parallel processing.
Exactly. If you're looking to quickly get a handle on how, all your devices juggle so many tasks, this is for you.
Right. We want to help you understand the core ideas without getting totally bogged down in details. So our mission here is to pull out the really crucial stuff about concurrency and parallelism.
We're talking history, theory, the hardware side, and how we even measure if it's working well.
Think of this whole deep dive as your streamlined guide. We've done the heavy lifting through the research so you get the key insights efficiently.
Precisely. It's your audio study guide, aiming for a clear, structured understanding. Good if you're brushing up, figuring out performance issues, or, well, just curious about what makes modern tech tick.
Okay, let's jump in. First up, definitions. We need to get clear on concurrency versus parallelism. They sound similar, but they're not the same thing.
Not at all. Concurrency, at its core, is about structure. It's the ability to deal with lots of things seemingly at once.
Seemingly.
Well, yeah. The key is that a concurrent problem can be broken down into pieces that can run independently, or mostly independently, without messing up the final result. Think about threads in software. That's a common way to do concurrency.
Okay, structure. Breaking things down. And is that quote from Rob Pike?
Ah, yes. Concurrency is not parallelism. It's better. It's a bit provocative, but it highlights a really important point about design.
What's the point he's making?
That concurrency is about composing these independent processes. They communicate to coordinate, but they're designed as separate units. It's an abstraction that can actually make programs simpler and easier to reason about.
Right, simpler design.
Yeah.
Okay, so if concurrency is the structure, what's parallelism then?
Parallelism is about execution. It's about actually doing many things simultaneously, for real.
So like needing multiple processors or cores to pull it off.
Exactly. Parallelism is really a special case of concurrency, where those independent bits are physically running at the exact same moment on different hardware units.
Got it. So my analogy might be, concurrency is like a chef juggling multiple pans on one stove, maybe switching between them quickly.
Yeah, that works. Our sources call it virtually parallel. The execution gets interleaved, time slicing. Sometimes they call it teethed execution.
Whereas parallelism is like having multiple chefs, each with their own stove, all cooking at the same time.
Precisely. That's the physically parallel part. Genuine simultaneous work.
Okay, that clears it up. So you can have concurrency on a single core machine, like juggling those browser tabs.
Right.
But you need multiple cores for actual parallelism, and that concurrent structure is what makes the parallelism possible in the first place.
You've got it. And concurrency isn't just theory, it's everywhere. Responsive UIs that don't freeze up, that's concurrency.
Real-time systems too, right? Like controlling machinery.
Absolutely. Simulations, animation, visualizations, and crucially, it's the foundation that enables parallelism for those really big compute-heavy tasks.
Okay, structure versus execution. Got it. But let's talk speed. Why the big shift towards parallelism for performance wasn't just making processors faster enough for a while?
It was for a long time. That was the Moore's Law era, basically. Higher clock speeds meant faster programs. Simple.
So what happened?
We hit a wall. Around the mid-2000s, maybe 2004, pushing frequencies higher just generated too much heat. Power consumption became a massive problem.
Right, the chips would just melt, basically.
Pretty much. Power use increases really fast with frequency, exponentially, in fact. So the industry had to change strategy.
From faster single cores to more cores.
Exactly. Multi-core processors became the way forward. Instead of one super fast core, you put several, reasonably fast cores on a single chip. That's when parallelism went from being a niche thing to being absolutely essential for performance gains.
I remember when dual-core chips first came out, like the Pentium D.
Yep. Intel's Pentium D around 2004, AMD's Turin 64X2 in 2005, those were key moments in that shift. And there's also Moore's second law,
Which is?
that the cost of building the chip factories, the fabs, goes up exponentially too. So finding better ways to use the silicon you can make, like parallelism, became even more important economically.
So parallelism became a necessity, driven by physics and economics, and the need for that compute power is huge in some fields.
Oh, definitely. Think weather forecasting, climate modeling, massive simulations.
Biology, genomics, drug discovery.
Yep. Astrophysics, modeling galaxies, computational chemistry, material science. And of course, AI and big data analysis are completely reliant on it now.
Okay, so we know what they are and why parallelism is dominant now. Let's switch gears to history. How do we even start programming concurrent systems? It sounds like it wasn't exactly easy at first.
Oh, far from it. The sources say concurrent programming kind of grew out of simulating multiple things using interrupts in early operating systems. Multi-programming, they called it.
But without a solid plan, I imagine.
Pretty much. These early systems were often written in assembly language, very low level, and crucially lacked a strong theoretical basis. And yeah, that led to problems.
Like bugs.
Lots of bugs.
Exactly. Crashes, unpredictable behavior. By the late 60s, operating systems had a pretty bad reputation. IBM's OS 360 is mentioned specifically. Apparently, it had serious issues with tasks getting stuck in deadlock.
Deadlock where everyone's waiting for everyone else.
Yeah, the deadly embrace.
Wow.
Tasks would compete for resources and just get jammed, waiting indefinitely. Sounds like a nightmare to debug, a real bug-squashing bonanza, as you said earlier.
Definitely frustrating. So this mess actually spurred research into the theory behind it all.
Precisely. The initial motivation was just making operating systems reliable. But scientists quickly realized these ideas about managing concurrent tasks applied much more broadly to any kind of parallel computing.
And that led to some foundational work in the late 60s and 70s.
It did. Several really key papers emerged. Dijkstra's Cooperating Sequential Processes from 1965 is a big one.
What was the breakthrough there? Dijkstra really laid the conceptual groundwork. He stressed that cooperating processes should be loosely coupled, interacting only at specific, defined points. And critically, he said you cannot make assumptions about how fast different processes run relative to each other.
Speed independence. That sounds vital for correctness.
Absolutely. His paper set out principles for managing these independent processes so they'd work together reliably, regardless of speed variations.
And he defined some core concepts too, like mutual exclusion.
Yes. Mutual exclusion, only one process in a critical section, the code accessing shared stuff, at a time. Fairness, everyone eventually gets a turn. And that speed independence we mentioned, pausing a process outside its critical part shouldn't break things.
Okay, setting the basic rules of engagement. Then came his 1968 paper on the ESI-E system.
The structure of the multi-programming system.
Yeah.
He introduced a layered system design, like a hierarchical abstract machine, and importantly, he introduced semaphores.
Semaphores, those are for synchronization, right?
Exactly, a fundamental tool for synchronization and communication between processes. He also started formalizing how harmoniously cooperating processes should behave, things like tasks eventually finishing and the system reaching a stable state.
Building blocks for reliable systems. And then another paper in 71.
Hierarchical ordering of sequential processes. He refined his ideas further and introduced the famous dining philosopher's problem.
Ah, the philosophers trying to eat spaghetti with shared forks. Classic deadlock example.
Classic deadlock and starvation example, yeah, where a process might never get the resources it needs. He also talked about data encapsulation here, hiding shared data, which kind of points towards the idea of monitors later on.
So Dijkstra laid a huge amount of groundwork. Then C.A.R. Hoare entered the picture in 71.
Right, towards the theory of parallel programming. Hoare focused more on principles for designing parallel languages.
Like how to build safety into the language itself.
Exactly. He talked about controlling interference, catching time-dependent bugs early, ideally at compile time. He pushed for disjoint processes, no shared mutable state, explicitly declaring shared resources, using critical regions for access, and conditional critical regions that wait for conditions to be true, trying to structure programs to avoid common concurrency errors.
Makes sense. And then his big one in 78, communicating sequential processes, CSP.
Huge influence, yes. CSP proposed a different fundamental model, composing programs from sequential processes that communicate explicitly, typically through synchronous message passing. He defined a formal language, also called CSP, for describing these interactions.
And that influenced actual programming languages.
Massively. Occam, Erlang, and very notably, Go.
Ah, Rob Pike again.
Yeah.
The sources mention Go's concurrency model is built on CSP ideas.
It is. Pike himself pointed out how cleanly CSP concepts could be added to a C-like language. It provided powerful concurrency without, forcing huge changes on the rest of the language, kept the core ordinary, as he put it, while adding this powerful concurrent layer, orthogonal design.
Fascinating how those abstract ideas from decades ago directly shaped languages we use now. The sources also list a whole bunch of other contributions over time.
Yeah, it's like a timeline of problem solving. After the basics, researchers tackled specifics, mutual exclusion with different kinds of registers, efficient concurrent reads and writes, distributed systems challenges like state machines, and Byzantine failures.
Byzantine failures where components might lie or give conflicting info. Sounds tough.
Very tough. Then ensuring liveness, proving limits like the impossibility of distributed consensus under certain conditions, faster algorithms, weight-free approaches, transactional memory. It goes on.
Transactional memory sounds like databases.
Similar idea, applying atomic transactions to memory operations. Then robust sharing and message passing systems, consensus with failures, even distributed recursion up to 2010. It's a rich history.
Like building layer upon layer of understanding. And the source mentions the Dijkstra Prize for finding more details.
Exactly. A great place to look for landmark contributions in distributed and concurrent computing. It really shows how foundational that early work was.
Okay, history covered. Let's get into the how it works now theory and architectures. We need some terminology first.
Right, so concurrent processes, their execution overlaps. They can be disjoint, private data only, or interacting, shared data.
And synchronization.
That's the umbrella term for controlling the order of operations. Precedence, priority, mutual exclusion, it's all synchronization.
And monitors.
A monitor is a programming construct. It bundles shared data with the operations on that data, guaranteeing only one operation runs at a time, mutual exclusion, and providing ways to manage process synchronization. Builds directly on Dijkstra and Hoare's ideas.
Got it. Essential vocabulary. Now, how about the types of parallelism?
Well, you can classify it a few ways. One is by the computation mechanism. Vector parallelism uses special hardware to do the same operation on many data elements at once.
Like in GPUs.
Exactly. And then there's thread parallelism, which uses separate software threads or flows of control.
And the other classification?
Is based on regularity. Regular parallelism involves lots of similar tasks, predictable dependencies. Think image processing. Irregular parallelism has more diverse tasks, less predictable dependencies, maybe like graph algorithms.
And real apps often mix these.
Very often, yes.
Yeah.
And a crucial point-efficient serial code is still incredibly important as the foundation. Parallelism doesn't magically fix slow sequential parts.
Good reminder. Now, before hitting parallel architectures, the source mentions the von Neumann machine. Why bring up this old design?
Because, fundamentally, most individual processor cores still operate on von Neumann principles. It's the bedrock, proposed way back in 1945.
Still relevant.
Absolutely. It's Turing, complete, well understood, the standard for decades. CPU with logic unit, control unit, memory for both instructions and data, I/O. That basic model persists even inside complex parallel systems.
The basic building block we replicate. Okay, now for abstract parallel models, RAM and PRAM.
Right. RAM, the random access machine, is the theoretical single processor model based on von Neumann. Used a lot for algorithm analysis. CPU, input, memory, output. Simple.
Then PRAM.
Parallel RAM extends the RAM model. You have multiple CPUs, all connected to one big shared memory pool via a common bus. It's a theoretical tool.
And there are different flavors of PRAM depending on memory access rules?
Yes, how they handle simultaneous reads and writes. CRCW allows concurrent reads and writes. CRW is concurrent reads, exclusive writes. ERCW is exclusive reads, concurrent writes. And ERW is exclusive everything.
So exclusive means only one at a time.
Exactly. These models help analyze algorithms under different assumptions about memory contention, like can multiple processors write to the same spot at once or not?
Theoretical tools. What about real hardware? The source mentions a big shift from shared memory to distributed memory for scaling up.
That's key. In the late 80s, early 90s, shared memory machines where all CPUs access one memory pool started hitting limits, maybe a few dozen processors max.
What are the limits?
The pathway to memory, the bus or network, becomes a bottleneck. Too many processors trying to access it at once.
So distributed memory took over for large scale.
Yes. Each CPU gets its own private memory. If they need to share data, they explicitly send messages over an interconnection network. The design of that network, its topology, becomes critical for performance.
Which brings us to Flynn's taxonomy, a classic way to categorize architectures.
Still very useful. Michael Flynn proposed it in the 60s. Classifies hardware based on instruction streams and data streams. 4 main types: SISD, SIMD, MISD, MIMD.
Okay, let's break them down. SISD.
Single instruction, single data. Your standard single processor computer, one instruction stream, one data stream. Though modern ones use internal tricks like pipelining to get some parallelism inside.
Right. Semi-empty.
Single instruction, multiple data. Multiple processors execute the same instruction, but on different data. Think vector processors, GPUs, or those AVX instructions in CPUs. Great for data parallel stuff.
The MISD, the less common one.
Multiple instructions, single data. Multiple instructions operate on the same data stream. Pipelined architectures can be seen this way. The source mentions Space Shuttle Flight Control Systems as an example, not mainstream.
MOMIMD.
Multiple instruction, multiple data, the most general, most common for parallel systems, multiple processors running different instructions on different data, all independently. They need software to coordinate.
And IMD can be shared or distributed memory.
Correct. Most supercomputers, servers, even our multi-core desktops are IMD. There's also SPMD single program, multiple data.
How's that different?
It's a programming style often used on IMD machines. All processors run the same program code, but operate on different chunks of data, often easier to manage than having completely different programs on each core. MPI, the message passing interface, is common for SPMD on distributed memory.
Okay, that taxonomy is a helpful frame. Let's dive deeper into specific techniques. Pipelining.
Like an assembly line for instructions inside the CPU. Break instruction execution into stages. As one instruction moves to the next stage, a new one enters the first. Increases throughput, more instructions finished per second.
But does it make one instruction faster?
Not necessarily its latency, no, but you get more done overall. You have pipeline registers between stages. Sometimes you get stalls or bubbles if an instruction needs to wait for data.
And superscalar.
Takes pipelining further. Multiple execution units, fetching and dispatching multiple instructions per clock cycle. More internal parallelism.
Vector architectures? Sounds like SEMD.
Very much related. Designed for operating on whole arrays or vectors of data very efficiently. Cray supercomputers were famous for this. Deep pipelines, vector chaining. Feeding the output of one vector operation directly into the next one, avoiding memory. GPUs today use similar ideas with their shader pipelines for graphics and general computation. And those SIMD extensions like MMX, SSE, AVX brought vector-like processing to standard CPUs over the years.
All right, the whole history there. Now back to MMD shared versus distributed memory details.
Okay, shared memory MIMD. Multiple processors, one shared memory space connected by some network. Simple versions use a bus.
The bottleneck problem again.
Yeah, the bus gets saturated. So systems use caches heavily to reduce bus traffic. More complex systems use faster hierarchical interconnection networks instead of a simple bus.
And distributed memory.
Each processor has its own private memory. Communication happens via explicit message passing over a network. That network can be static, fixed links, or dynamic.
Connecting every processor directly is too complex.
Prohibitively expensive for large systems, so you use simpler topologies, rings, meshes, hypercubes. In MMA, non-uniform memory access is common, where accessing local memory is faster than accessing remote memory.
Okay, and finally, the source lists other parallel programming models.
Yeah, beyond shared distributed memory, there are different abstractions. The actor model uses message passing between independent actors. Bulk synchronous parallel, BSP, has computation phases separated by synchronization barriers. CSP we mentioned. Data flow models, functional approaches, PRAM, SPMD PGAS. Lots of ways to think about and structure parallel computation.
A really diverse toolbox for complex problems.
Yeah.
Okay, we understand the machinery. Now, the big question. How do we measure if all this parallelism actually helps? How do we quantify the performance gains?
Right, performance analysis. The basic metrics are speedup and efficiency. Speedup SP is just runtime on one processor, T1, divided by runtime on P processors, TP. So SP equals T1, TP.
Higher is better.
Higher is better. And efficiency, EP, is speedup divided by the number of processors. EP equals SPP. It tells you how well you're utilizing the extra processors. An efficiency of 1 or 100% means perfect linear speedup.
But achieving that is hard.
Very hard. Performance depends on the hardware, the problem size, the input data, lots of factors.
So we need theoretical models.
Yeah.
Amdahl's law comes first.
Yes, Jean Amdahl's observation. It gives an upper limit on speedup for a fixed size problem. The key idea is that some part of any program is inherently serial. It just can't be parallelized.
The sequential bottleneck.
Exactly. Let's say sigma is the fraction of the code that's serial. Then 1 is the parallelizable fraction. On P processors, the serial part still takes T1 time. The parallel part ideally takes 1 T1 P time.
So the total time TP is T1 plus 1 T1P?
Yes, yeah, and the speedup SP equals T1 TP, which simplifies to Amdahl's law, SPA 1 plus 1P.
And the crucial implication.
As p gets huge, the 1p term goes to 0. So the maximum speedup gets limited to 1.
So if 25% of the code is serial 0.25, the max speedup is 1.25 is 4x no matter how many processors you throw at it.
Exactly. That serial part becomes the ultimate bottleneck. Efficiency drops towards 0 as p increases. It's like that analogy of painting a house. If one big room takes one person a long time, adding more painters for other rooms only helps so much.
So Amdahl's law seems a bit pessimistic, especially for embarrassingly parallel problems where cha-cha is tiny,
It is, for fixed workloads. But then comes Gustafson's law.
offering a different perspective.
Yes. John Gustafson noticed that when people get bigger computers, they often run bigger problems, not just the same problem faster. The workload scales up.
And maybe the serial part doesn't grow as fast as the parallel part.
That's the key insight. Gustafson's law looks at scaled speedup. It asks, how much more work can I do in the same amount of time if I have P processors?
How does that work?
It uses ES for the fraction of parallel runtime spent on serial work, and P for the fraction on parallel work, S plus P equals 1. The scaled speedup is then SP equals S plus PP, or SP equals P plus 1 PS.
So if the problem scales and S stays small, the speedup can keep growing with P.
Potentially much more linearly than Amdahl suggests, yes. If S 0.5, half the parallel time is serial, and P equals 4, Gustafson gives SP equals 4 plus 1, 4, 0.5 equals 2.5. It's more optimistic when workloads scale.
So Amdahl is glass half empty for fixed problems. Gustafson is glass half full for scaled problems.
A good way to put it. Reality often involves overheads too, thread creation, locking, load imbalance, which neither simple law fully captures.
Okay, so there's another model, the workspan model, using graphs.
Right. It uses directed acyclic graphs, DAGs, to map out tasks and their dependencies. It acknowledges that dependencies limit parallelism.
What are the key concepts?
Work, T1, is the total computation, like the serial time. Span T infinity is the length of the longest path of dependent tasks in the DIGA. It's the theoretical minimum time, even with infinite processors, also called the critical path length.
And how does that relate to speedup?
It gives an upper bound, speedup work span xt1t. This is often a tighter bound than Amdahl's because it considers the actual structure of the computation's dependencies via the span.
And Brent's lemma.
Brent's lemma relates the actual parallel time TP on P processors to work and span. TP ET1P plus T.
What does that tell us?
If the span key is much smaller than the work T1 divided by P, then TP is dominated by T1P, meaning you can get close to linear speedup. But TTHL always sets a fundamental limit. No matter how many processors P you have, TP can never be less than TTHL.
So minimizing the span, the critical path, is really important for scalability.
Absolutely critical, even more so than just minimizing total work sometimes.
Could we see an example? Like adding numbers.
Sure, adding n numbers serially. Work T1n, span Tn. Bad parallelism.
But if we do it in parallel, like pairwise sums in a tree structure.
Right. The work T1 is still about n, same number of additions, but the span T1 becomes roughly log 2n, the height of the tree, much smaller.
So Brent's lemma gives TPANP plus log 2n.
Approximately, yes. For large n, the NP term dominates if P isn't too huge, suggesting good speedup. But the log 2n term shows the limit imposed by the span. If n16, P4, T1 is 16, T1 16, 4, then TP164 plus 4 plus 4.
So the workspan model gives a more nuanced view based on dependencies. It highlights the importance of the critical path, the span.
Exactly. And it shows why doing slightly more total work might be okay if it drastically reduces the span. It also implies, under its assumptions, that you can't get superlinear speedup faster than P times with P processors.
Right, no magic bullets there.
It provides a solid framework for analyzing parallel algorithms by looking at the computation structure.
Well, that was definitely a deep dive. We've covered a lot of ground. Started with the basic difference between concurrency, the structure, and parallelism, the execution.
Then we walk through the history, seeing how pioneers like Dijkstra and Hoare developed the theoretical foundations, tackling problems like deadlock and synchronization.
We looked at the hardware side with Flynn's taxonomy, pipelining, shared versus distributed memory architectures. A whole zoo of parallel machinery.
And finally, methods to measure performance. Speedup, efficiency, Amdahl's law for fixed problems, Gustafson's law for scaled problems, and the workspan model looking at dependencies and critical paths.
Hopefully, walking through this, treating it like a study guide, has given you, our listener, a solid, structured grasp of these really vital concepts. We aim to hit the highlights without the overload.
Exactly. A foundation for understanding how modern software and hardware work together to handle complex tasks. And maybe for digging deeper if you're interested.
And to leave you with something to think about, we're seeing increasingly complex computing tasks, AI, massive data, but we're also hitting physical limits on processor speed. So how will this interplay between concurrency strategies and parallel hardware evolve?
What new programming ideas or hardware breakthroughs might we need to unlock even more computational power? It's a fascinating challenge for the future of computing.
Definitely something to ponder. Thanks for joining us on this deep dive.